So have you ever had a question that you just couldn't get out of your head until you answered it? I've managed to nerd snipe myself just a touch, and that's what this video is about, answering a very important question that really isn't that important. You see, I've designed a few ESP32 PCBs, and recently I've used a couple of different voltage regulators. So one of the PCBs is this thing, which is for a espresso scale, a connected Bluetooth scale, and then this one, the most recent one, where I designed a freezer monitor, and on one of them I used a regular linear low dropout voltage regulator, and on the other one I've used a nice switching regulator from Texas Instruments. And whenever I did that, I thought that that switching regulator would be really efficient and maximize battery life. I selected that part actually because it's supposed to have extremely low power draw. Now, I also selected the linear regulator to have low power draw, but I was really surprised whenever I started measuring the deep sleep power draw of those circuits, just how low of a power draw that linear regulator had. And it led me to think, well, maybe my conception of what's going on is a little skewed. And the more I thought about it, the more I thought, I bet that that switching regulator is more efficient maybe at higher power draws, but at really low power draws, like what an ESP32 draws in deep sleep, maybe the linear regulator is more efficient. So that's what these little boogers are for. Because to answer this question, I designed a little circuit with both of these regulators so that I can actually test their power consumption. Now, this is what I mean where this is really not a big deal. This is not necessarily something that a lot of people are going to care about because it's pretty niche, but I cared about it far more than I should have. So I spun up some PCBs and let's just test it and find out. All right, so we got you good and zoomed in so that we can show you what's going on here. So this little board I made, you can see we've got the power input coming in, and then I've got two voltage regulators, one on the left and one on the right. And you can see I've got this little pin array that I can jumper back and forth on the inputs of these two chips. So what are the two chips that I went for? Well, over here on the left, this is a Torex part. It's a regular linear voltage regulator. You can see it's only got the input cap and the output cap, so it's a very low part count. This specific part is a XC6210B332. It can do up to 700 milliamps out at 3.3 volts, and it can take up to a 6 volt input. Over on the left, this is the switching regulator that I'm using. It is a Texas Instruments TPS62A01, and it has a slightly higher part count. You can see input capacitor, output capacitor, and then you've got these two resistors that form a voltage divider that help set the output voltage, so you can adjust it by changing those resistor values. And then this big chunk right there is the inductor for the output. Now on the other side here of this board, you'll see the output comes from the middle pin, and so I can jumper that back and forth to bring the output of either voltage regulator over. And so that means that I can use these pins here to jumper back and forth between these two. So this big resistor here is my dummy load. This is a 100K resistor, and on a 3.3 volt output here, this should provide about 33 microamps worth of load, which is very similar to the last ESP32 board I made in deep sleep. And so this is going to be basically simulating a deep sleep load. And if I want to add more load, I've got this other output here, and so I can wire in basically extra resistors, so I could use a much lower value resistor to get higher power draw if that's what I really wanted. And so this will allow me to switch back and forth between these two parts and to adjust the output load. And it was pretty cheap to make, but I've got a few extra because even if I only need one to test, it was cheap to make extra because you can only order these in batches of 5 anyway. And it gives me voltage regulators that I can use in other projects if I need to. So let's get into some testing. Okay, so let's do a low power test. So I've got the power supply set for a 4.2 volt output, and I'm running into the linear regulator side. Got everything hooked up, and so I'm going to use the fluke to measure the current that goes through. So on this thing, the load is going to be roughly 33 microamps, depending on the voltage output, but let's give it a shot. And about 41 microamps on the output, which means got about 8 microamps of overhead, more or less. So let's check voltages real quick, just to make sure that the output is what it should be. And I've got 3.351 volts. And so now I can stop this, flip the jumpers over to the other side real quick. And now I can check at this low power draw what the switching supply does. And this is actually what I suspected. So at this low power draw, we've got 54. So an extra 14 microamps on that switching supply. Now, I'm gonna try to do this at a few different voltages and see how these things change. Let's go to 3.5 volts. This will simulate kind of a dying battery situation. We'll see kind of what the regulated output looks like. So here we go. And so we got closer to 60 microamps, which again, lower voltage on the input might cause some strange. Let me, I haven't measured the output voltage, 3.392. Okay, and now let's test the 3.5 volts with the linear supply, or the little linear regulator rather. 41.82, and the voltage is 3.35 volts. So kind of interesting overall. What I found is the linear regulator actually draws less current and the voltage is a little more accurate. So yeah, interesting. Now I can go up to 5 volts on this thing and that should be fine. So at the 5 volt input, I'm getting about 40.5, 40.67. Boy, that's rock solid. And then again, if I go down to like 41.3, so it seems to be pretty stable. Yeah, the higher the input, the lower the current, but it's not really that dramatic. Whereas the switching regulator, we're up to almost 60 microamps at 3.5 volts. We got 55.5 at 4 volts, and at 5 volts, 49. So it seems to also be more sensitive to the voltage input than the linear LDO. So after the first test, yeah, it does look like that linear voltage regulator is more efficient at very low current draw situations, such as when you're in a deep sleep situation on battery with an ESP32. Which means for me, for those projects where what I'm really doing is trying to make a device which is asleep the vast majority of the time and only wakes up briefly, and then it bursts out some data on some readings, then goes back to sleep, that linear regulator is going to be more efficient. Now, the next question is, what about higher power draws? Because it could be that the linear regulator is more efficient in deep sleep, but whenever the thing comes awake, it might be less efficient. And it's possible because of the dynamics of efficiency and power draw that the power losses at high power draw could actually outweigh the power savings at low power draw. So let's do some other tests and find out. Okay, so on to round 2 of the testing, where I'm gonna try to run a bit of a higher power draw to see at, that higher level whether the efficiency of these two regulators changes. So for the load, I have an ESP32 running as much power as I can get it to pull. Basically, I'm loading up both cores with a bunch of arbitrary math, and I'm also firing the Wi-Fi and BLE radio as much as possible, trying to scan and do connections and all kinds of stuff. And if you're not aware, because of the way the system works in the ESP32, the radios won't stay on nonstop. That just the way the Wi-Fi and Bluetooth work, it does it in pulses. So I do want to show you something that may or may not be interesting. I'll show you the thermal camera that I have, and I'll put that on this ESP32 just so you'll see I really am working the crap out of this ESP32. You can't see it on the front, but on the back, you can really see ESP32. You got a good little hot spot there. I can actually feel it getting a little warm. Now it's not hot, and that's one thing I would point out, like it's not hot, but it is working. That ESP32 is doing some business. Now you can't see it because that can reflects all the infrared. Yeah, 93 degrees Fahrenheit, and I mean, it's like 70 in this room. I've got the power meter in an averaging mode, so we can see the average power mode. Got the power supply set for a 4-volt input, and I don't think I'm gonna test too much at various input voltages. I'm mostly just gonna see what happens at 4 volts because that's kind of a charged LiPo battery. So fire the thing up. Let me make sure it boots correctly. Sometimes there's a bit of a soft start. And reset. And there we go. So you can see, again, it will fluctuate on the power draw. The peak, I think that's the startup peak. It's not really pulling that much. At any point. Generally speaking, the ESP32, it'll boost up to like 250 to 300 milliamps. But yeah, so we're getting 98.5 on average, 99. So yeah, that's with the linear regulator. And so now let's switch over to the other regulator and see what we get. Okay, so we've swapped over. Okay, so with the switching regulator, it does look a little higher. So this is where I really expected the switching regulator to be a little bit more efficient at higher power levels. Because again, that previous load was super, super light. You know, 33 microamps was kind of the intended load. And this one, you know, you're looking at 100 where, yeah, it's 4 or 5 milliamp higher power draw at the same voltage input and the same load on the output. So really interesting. I didn't expect this. I wasn't surprised at the lower power draw that the linear regulator was more efficient because it doesn't have the voltage divider and that will pull a little extra power. But this is surprising. Now this isn't huge. You know, you're only looking at a few % of efficiency difference here. But still, given, you know, the thing is the Texas Instrument part, it has more complexity. You need more components. It's going to be more costly to implement. And based on this, it doesn't look like it actually is going to be worth it for any of the uses that I have for it. It's just not efficient enough to warrant the extra complexity of the design and the cost. It's actually less efficient. So this is kind of a double win for the simple linear voltage regulator. Again, for the type of designs that I'm going to be doing. Now, it may have advantages somewhere else. And certainly you can get the same Texas Instruments regulator with much higher outputs. You can get like 2 amp versions of that thing. So it's got that going for it because it can be very small and still handle a lot of power. But I don't draw a lot of power on ESP32 projects. And so, you know, now we're up to 101, 101 and a half. So yeah. It looks like the linear regulator is the way to go for me. And I guess I was curious, so I popped the voltage down to 3.6 volts. You can see right here, just to see if the efficiency really changes at low voltages as the battery dies. Doesn't look like a huge difference. This is the switching regulator. It's at, you know, 99-ish, which is, yeah, it was a little higher, actually, at the higher voltages. So that was kind of interesting. It should be the opposite. It should have to draw more current at lower voltages. But let's stop it and flip it over and see if the linear regulator is any different. It's back over to the linear regulator. I thought about putting switches to do this, like dip switches, but I couldn't find dip switches that would handle the current. And also dip switches are surprisingly expensive. So we're back over to the linear regulator now and click it on. It's still not drawing as much power as the switching supply. So yeah, even at low voltage, it doesn't really matter. The linear regulator is just better. You know, and if I wanted to, I guess, fulfill the whole test, I could go up to 5 volts and just do it at the high level again. So interesting there that it draws 110. Because again, I would think at the higher voltage it would need to draw less current, but it may have to work harder to step that voltage down. Because it's up to 109 milliamps. Let me see. So that's linear. Let me flip over to the switching. Yeah, so there's a bit of an inverse relationship with the switching regulator. It gets more efficient with a higher input voltage, whereas the linear regulator gets a little less efficient at a higher input voltage. So I think it's just that linear regulator has to work harder to drop the voltage more, whereas the switching regulator does seem to handle that high input voltage quite a bit better, and it gets a substantially lower power draw. So there may be some nonlinear interactions here where, you know, some of the things that I've said may not hold at all levels. Now, the problem with this is 5 volts isn't coming from a LiPo battery. LiPo battery, you're only going to be getting at most, you know, 4.2 here. And if I do 4.2, and so this is kind of the thing at battery levels, which that's where this is important. The linear regulator is better. So I think that's where this is. Okay, so that was also kind of surprising. Now, it could be that the power draw is still low enough that that switching regulator hasn't hit the real kind of where it's the most efficient. Because I think with a lot of switching power supply stuff, it really is most efficient towards the top end of its capabilities. And even at 200 or 300 milliamps, that switching regulator can do up to an amp. So it could just be that the ESP32 devices that I'm using aren't really pushing the thing hard enough to warrant using that part. Because yes, it might be more efficient at even higher power draws, but I'm never getting there. The average power draw is 100 milliamps, give or take, and that's just not in the range where that device is going to be super efficient. So the reason kind of why this matters is the part count and pricing really comes into play. So depending on what time you're looking to buy these products, the switching regulator is usually more expensive. Now, currently, whenever I pulled up the prices on JLC PCB, the linear regulator was actually quite a bit more expensive, but there was a break even because the switching regulator requires extra parts, and some of those parts are not going to be basic parts the way JLC PCB pricing works. That means you get charged an extra $3 for every extended part you use. And with 2 extra extended parts, that's $6 on your order just to use that regulator, which means you could make over 100 boards with the linear regulator, even at a higher price per regulator, and still come out ahead. And as a matter of fact, once you include the fact that, well, if you're spinning up that many boards, you start to hit volume pricing, and in volume, the gap just widens, so that I really think there's no place on my designs where the switching regulator is actually cheaper. Plus, it's less efficient, which means I guess I'm just going to go back to the basic linear LDO stuff. It's easier, it requires fewer parts, and whenever I've ordered these in the past, it is also usually cheaper to go with a linear regulator. Now, not every set of regulators are going to work out like this. These are the 2 specific ones that I've been using, and so that's why I did this test for myself. I don't expect a lot of people to care about these particular 2 voltage regulators, but it's something to think about if you ever do PCB work. Voltage regulator efficiency, it's got some dynamics at play, and I've certainly learned a lot. Like I said, it's a bit of a nerd snipe situation where I got sucked into a problem and I just really wanted a good answer for it. And now I know. Not that this will really ever benefit and pay for itself, because, you know, I spent, I don't know, 35 bucks getting these boards made or something, and there's no way I'm ever going to make up $35 on savings in my designs, but, you know, still good to know. Anyway, I hope you learned something. I sure did. As always, if you got feedback, comments, suggestions, love to hear them. Feel free to leave it down below. As always, I appreciate your time. Thanks.